I'm going to wait one more minute as people continue to join the webinar. So we'll get started here in just a second. All right, Michael, can you advance to the next slide? I want to welcome everyone to today's technical webinar from FREEDM. My name is Ken Delaney, and I'm the Director of Industry and Innovation at FREEDM. We are a power systems and power electronics research center at North Carolina State University. Our research projects span renewable energy integration, electric vehicle technologies, control techniques, microgrids, and applications of wide bandgap semiconductors, and of course, traditional power systems analysis. We have extensive lab capabilities, including multiple simulation labs for HIL development, an electronics packaging lab, and a high bay lab for evaluating medium voltage applications up to 15 kV AC input. Together with our industry partners like ABB, Duke Energy, Meta, and the New York Power Authority, we are leading the electrification revolution. Hopefully, everyone is familiar by now with Zoom. We have disabled audio and video for all attendees, and we ask that you use the chat feature to ask questions. Just hover your mouse over the Zoom window and the button should appear at the bottom of that window. Click chat, type your question, and we'll answer as many as we can. Note that this webinar is being recorded and will eventually be posted to the YouTube channel for the Department of Electrical and Computer Engineering at NC State. And I will now turn the presentation over to our presenter. Michael, stage is yours.
Thank you. Hi, everyone. My name is Michael Kircher. I'm a student here at North Carolina State pursuing a PhD in power electronics. And today I'm going to be discussing the design, simulation, and testing of a high power traction inverter for heavy duty truck applications. So the agenda for today, first I'll give a little background on the intended application for this inverter and what it's going to be used for. Then I'll talk about the selection of the power semiconductor device, starting with some thermal simulation and loss analysis, and then a drive cycle simulation for the entire vehicle. Then I'll discuss the analysis that was done to select the optimal current sensor for our inverter. I'll compare a couple of current sensor topologies, and then give a system level performance simulation. Then I'll show you two prototypes that were built and tested at FREEDM. And finally, I will show our process for power testing the inverters, both just verifying functionality and measuring the efficiency at full power output. So this inverter is meant to go into a Class 8 semi-truck, which is the largest weight classification of 18-wheeler at greater than 33,000 pounds. And this truck is meant for a very specific application. It's to transport goods locally from a shipping port to a warehouse that's in town. So this will be short, relatively low speed runs, not a long distance highway traveling vehicle. And the target range is about 250 miles. Each night, the truck will return to the same place for charging. The US Department of Energy is the funding source for this project. And during this project, we also partnered with Ricardo Incorporated, our industry partner, who will be producing this inverter once the design is completed. A little detail about the drivetrain. This truck will be using an 800 volt nominal battery system that ranges from about 650 volts to 850 volts from empty to full charge. It is a complete battery electric propulsion system. There will be a dual E-axle setup. So in a semi, there are 2 drive axles, and each one has its own power source. And they are each one 250 kilowatts continuous power. Target efficiency for the inverter is 98.5%. And this E-axle assembly, which I've shown here, is an integrated axle, differential, and motor. And then the inverter is remotely mounted nearby on the frame of the chassis. So for the power device selection, the first step is to narrow down the possible power devices by looking at the worst case scenario operating conditions. So that's at our max power output and maintaining that peak efficiency of 98.5% at 250 kilowatts. Our phase current in this scenario will be 350 amps RMS, and that's at the minimum DC bus voltage expected of 650 volts. That's the highest stress scenario. Our target switching frequency is between 10 and 50 kilohertz. And that was a design parameter that we were able to change so we can optimize that switching frequency for minimal losses while still maintaining the form factor that we want. So I've shown here the 3 top contenders of semiconductor devices. There were a wide range of ones that we analyzed, but these were some of the 3 best performing ones. First, we have the Danfoss DCM1000X module. This module, like all of the ones we looked at, were 1200 volt and 175C rated. This particular one is 660 amps, and it had the lowest on resistance of all the ones we analyzed at 2.1 milliohms. Next was the Wolfspeed XM3 series of modules. These modules come in a couple different current ratings, and they're all using the same die. So the different current ratings are just a different number of dies in parallel. And this allows us to analyze the losses for each one of those versions and see how that affects things. Depending on the switching frequency, the lower or higher current rated modules may be more optimal in terms of losses. As you go to more dies in parallel, you increase the current rating, but the switching loss goes up as well. And then finally, the microsemi module has the highest current rating of all of them by a significant margin. This was kind of our safest option and gave us the greatest amount of current leeway, but also, of course, is the most expensive module of those analyzed. So our first step in looking and comparing these modules was to do a thermal analysis under worst case conditions to determine whether each module would be feasible at all. Would they work or would they overheat at our worst case power output scenario? And to do this, we used PSEM. PSEM has a relatively new feature where you can do detailed data input for your device model. So for each of these characteristics, for example, the first one, BDS versus IDS, you can actually transfer directly from the data sheet the operating curves just by tracing them over a photo image. So this gives a more fine resolution on your curve fitting than typical simulation. Here are a couple examples of the data we were able to get out of that sort of simulation. On the left, we have for the 3 Wolfspeed modules, curves showing the maximum output current that's possible without overheating versus the switching frequency. So this kind of shows what I was discussing earlier. At low switching frequency, the highest current rated modules have the greatest output capability. That's pretty intuitive. More dies in parallel means you're lower on resistance and so less losses. But as you move up to higher switching frequencies, those higher current rated modules actually have less output capability due to the increased switching loss causing heating. The plot on the right shows the power loss versus switching frequency for 3 different modules that we looked at. And as expected, power loss increases pretty linearly with switching frequency. So this shows 1/2 of the trade-off between, for selecting switching frequency, the trade-off between power losses and the physical size of your passive components. As you increase in switching frequency, your power losses will increase significantly, but that may be a worthwhile trade-off for smaller passive component size. So once that worst case feasibility was passed, the next step was to do a driving cycle simulation to determine how the modules would perform in real world conditions and what their efficiency would look like. So to do this, we need to look at a drive cycle, which is a speed versus time plot. There are a couple different ones that are pretty standard in the automotive industry. They're based on typical driving behavior on a certain road. In our case, because our truck had such a specific intended use case, we were provided a drive cycle for that exact route. Some other data that's needed to do this overall system simulation is information about the motor efficiency at different torque and speed points. And then also a dynamics model of the vehicle, which includes things like its rolling resistance, aerodynamic drag, and the weight of the vehicle, which is important for accelerating or going uphill. One problem with these drive cycles is that they are very lengthy. For example, ours was about 3.5 hours long. And when you consider this period of time versus the minimum time step needed to do a thermal simulation of an inverter that's switching at tens of kilohertz, that quickly turns into a sort of impossible simulation. So there needs to be some way to condense down this data to speed along the simulation process. So we were able to do that pretty effectively by looking at where the most common operating points are. For example, in our drive cycle, we found that in these 2 operating ranges, 37% of the total driving cycle time fell into those ranges. So since the speed and acceleration is relatively slowly changing in the drive cycle compared to the thermal characteristics, we're able to just simulate at those individual points to get an inverter efficiency map at various torques and speeds. And then we can apply this over the drive cycle rather than just grinding through the entire simulation end to end. So here I've shown the Simulink overall model of the vehicle. We have lookup tables for motor efficiency and inverter efficiency. This is the drive cycle. It's showing the motoring, or derived from the drive cycle, the motor, torque, and speed plots. And then the output of this, we can find the losses from the motor and inverter and overall efficiency. So here are the efficiency results. 88% efficiency of the motor over the whole driving cycle, just under 97% from the inverter, for an overall efficiency of about 85%. So with this information, we were able to select a power device that would work best for us, and that was the Danfoss DCM 1000X. Advantages of this module over the others were, first, that it had greater cooling capability. If you noticed in a previous graph, the Danfoss module actually had higher loss than, for example, the microsemi module, but it was better able to dissipate that thermal energy because of its integrated cooling fin structure. So a typical module will just have a flat surface on the bottom, and that surface mates with the top surface of the cold plate. But in this case, the cold plate actually has a cutout in its top, and these fins are lowered down into it to come into direct contact with the cooling fluid. So that eliminates the thermal resistance from the cold plate surface, as well as the thermal interface between the cold plate surface and the module case surface. Another advantage of this module was the layout, with the DC tabs all being arranged on one side of the module. We were able to source a capacitor that would have terminals that could directly bolt to these module DC terminals, meaning there was no bus bar actually involved in the commutation loop. So the only inductance in the commutation loop is from the internal inductance of these leads in the module and the ESL of the capacitor. So the end result was that our loop inductance was very low, less than 11 nanohenries. And loop inductance, if you're not familiar, is important because that inductance will cause a voltage overshoot at the switching instant. And so that's kind of the limiting factor for how high of a DC bus voltage you can go, is the DC bus voltage plus the overshoot cannot exceed the device's voltage rating.
Hey, Michael.
Yes.
Real quick, we have a question from Thomas in the chat. He noticed that the inverter efficiency is asymmetrical. It's higher in the positive torque region and lower in the negative torque region. What's the physical reasoning behind the asymmetry?
That is a great question. I may have to defer this one to Mingy, who did this simulation. Mingy, are you on?
Hi, this is Mingy. I believe this is because that one is from the motor operating point. So region and generating of the motor have different characteristics. So that's why I believe there is a symmetrical inverter efficiency table.
Great.
Thank you, Mingy.
Yeah, thank you. And one more question, Michael. What's the approximate difference in the thermal resistance value with and without those integrated fins for a typical module?
Excellent question. I might have to get back to you on that afterwards. It's been some time since I looked at it, and so I don't know offhand.
Okay, that's fine. Thank you.
If we can note down who asked that, I can try to get it back to them.
Yep, the chat will be recorded, so we'll respond by email.
Great.
Okay, thank you very much. Keep going.
So moving on a bit to our current sensor analysis. This is one of our research focuses in this project. In a high switching frequency silicon carbide inverter, such as this one, we're able to get tighter control due to higher control bandwidth. The faster switching cycles allow a greater control update rate. And to actually implement this, you need a similar increase in sensor performance. So sensor latency, bandwidth become very important. And also the increased EMI in a high switching speed inverter means that the sensor output could potentially be affected by that noise, reducing its accuracy. And so the sensor can easily become sort of a bottleneck for your control performance. For example, if you want to take full advantage of a 50 kilohertz switching frequency, you'll need faster than 20 microseconds sensor response. And then if you want to also use that main current sensor for overcurrent protection, you'll need lower latency yet. So to get a good comparison on sensor performance across different topologies, we wanted to have a uniform way of testing them. A typical current sensor data sheet lists the output rise time for a given current DIDT, a waveform like this one shown here. And while this is easy to measure, it is not so applicable to the actual real world performance because this is not a waveform you'd expect to see. So to try to get a more realistic measurement of the performance, we looked at the actual operating conditions, so a more sinusoidal current waveform, and also a waveform that includes a fair amount of noise, like you would see from the inverter. So latency is a bit difficult to measure under sinusoidal output conditions. We developed a couple different methods for measuring it. The first one is to measure the actual current with a reference sensor. And then the current sensor is connected to a microcontroller, which has a digital to analog converter on it. And we use that digital to analog converter to repeat out the signal measured by the microcontroller. And we can measure that then on the same scope that has the reference sensor. And so that's what I've shown here. And then to get the latency, just measure from the zero crossing point of the reference sensor to that repeated DAC output. To improve upon that, instead of relying on the digital analog converter, which may introduce some small amount of delay itself, or it may just not be available on the selected microcontroller, we can just use a digital signal out of that microcontroller that indicates the time of zero crossing. So that's what I'm showing here. And then finally, for current sensors that work based off voltage measurement, so shunt sensors, we can remove the shunt and use a signal generator with this ramp waveform where the shunt would be, and then sample that at the same frequency as this ramp waveform. So the sampling will occur at the same point on the ramp. If we then use a signal output to indicate the sampling instant, we can compare that sampling instant to the level of the ramp, and the time instant that that level is equal to the digital to analog converter output. So this eliminates any delay coming from the digital to analog converter, and we can measure the latency that way. This is our test setup for current sensor measuring. The prototype inverter was not ready at this time, so we used another silicon carbide inverter developed by FREEDM in the past. And the setup is fairly simple. We're using an inductive load in this case rather than a resistive or motor load, just for simplicity's sake, and because this allows us to use a pretty minimal in size DC power supply, since the inductor consumes no real power. Here I'll also highlight the current sensor that we were testing at this time is a pretty typical open loop Hall effect sensor made by LIM. This is very common in automotive applications for traction drive inverters. So here's the signal chain for that first sensor that I just showed. It's pretty straightforward. Sensor outputs a 0 to 5 volt analog signal that's just level shifted to what the microcontroller ADC wants to see, and then a small amount of filtering before going into the microcontroller. The next sensor we tested was a shunt-based design. It uses a delta sigma modulator and demodulator chip. And the purpose of that is to pass the signal through the digital domain where it can get galvanic isolation, since you need that common mode isolation between the shunt itself and the microcontroller. So this signal chain is a bit longer, and because it's modulating and demodulating, that chip has an analog output, which is then fed to the microcontroller in the same way. And then finally, we have a similar delta sigma modulator chip that then gives a direct digital output, which has to be filtered internally on the microcontroller to recover the analog value. The results of our comparison testing were that the most typically used in industry open loop Hall sensor has the lowest performance, a latency of 30 microseconds, which would be insufficient for making the most of high switching frequency designs. The sigma delta modulator only that does not demodulate has significantly better latency performance and slightly better resolution. But it is limited by the fact that it has to receive a clock signal from the microcontroller, and that clock signal is limited in frequency to maintain its integrity in the high noise environment. The modulator and demodulator integrated has the best performance because with the modulator and demodulator on a single chip, the clock speed can be an order of magnitude higher at least, which allows better demodulating, filtering, and less delay introduced from that step. So kind of in summary on the current sensors, it's important that the testing methodology reflects real world use conditions. And the latency measurement also needs to be taken across the full signal chain. So that's both the sensor itself and all subsequent filtering and signal processing that's required. And then finally, to determine whether this increased sensor performance is actually useful for us, it's important to do a system level simulation. So that's the controller, the sensor itself, and the hardware to determine if that increase in performance will actually help the system as a whole. So here's an example of that simulation. This is in Simulink. We have the sensor model. So that's including things like shift in accuracy, any delay, noise, etc. The current controller that would be implemented in the microcontroller software, and a sort of miniaturized version of a driving cycle, or just a short torque transient command. And then within the simulation, we have a Plex subsystem that models the inverter's hardware, as well as the traction drive motor, the PMSM. Here are the results from that simulation. On the top left, we have the current sensor simulated output. You can see this has more ripple than the direct current information. But the end result of this test is that because our external hardware requirements for the controller limit us to 10 kilohertz control bandwidth, the higher performing current sensors would not give us any benefit. So we can see here with no sensor model at all, just directly feeding the actual current into the controller, the torque output is indistinguishable from the torque output using measurement from these Hall sensors with the additional ripple and some delay. So in our case, higher performing current sensors were not necessary.
So Michael, your answer to that slide on the current sensor decision may actually impact Thomas's question here, but it's still a good question. Provided the motor currents are continuous CCM operation, what's the fundamental electrical frequency such that a delay from a current sensor would be significant enough to impact the performance?
Good question. I would say if you're talking about the fundamental frequency that the motor is seeing, that is less of a concern for current sensor delay. The delay from the current sensor will not be approaching that time scale. And so your control at the fundamental frequency should not be affected. But where this does come into play is during sharp transients, as well as dealing with harmonics in that current signal. So you will actually have harmonics up to at least the switching frequency playing a role in what the current sensor is measuring. And so typically we look for a current sensor with a latency less than 1 switching period. but also it depends a bit on how sharp of transients you expect to see in the torque command as well.
Great, thank you.
So moving on to the prototypes, this is the first prototype that was constructed. I'm showing a CAD model here so that you can see what's covered up by the circuit boards and the bus bar. On the right, we have the DC link capacitors. Unfortunately, due to some supply issues, we were not able to get the desired DC bus capacitor for this first prototype. This is a slightly smaller version of the desired capacitor. So we actually had to use 2 of them, and we were not able to bolt them directly to the module tabs. So that's the reason for this larger bus bar. Here we have an EMI filter on the DC bus. This is the gate driver board. Beneath it are the power modules. We have a mezzanine board here for the controller. And then the current sensors are kind of obscured by these terminals, but they're just beneath there. And I'll also note an annotated version of this will be available after the presentation. Shown here. This is the second prototype that was constructed. This is a much more finalized version. This will actually be put into trucks for road testing. You can see here we have the final version of the bus capacitor, which is bolted directly to the modules, which reside under this board. That gives us a very minimal inside DC size DC bus bar. This bus bar is now only responsible for carrying the DC currents because, again, it is not involved in the commutation loop at all. Here we have the same ferrite EMI filter, a DC current sensor, which is the LIM open loop Hall type. This board is for active and passive discharge of the bus. So in the event of a fault or total inverter shutdown, this will bleed off the voltage in the DC bus capacitor. This is the controller board, and the gate driver board and the modules are both underneath here. Just visible at the edge here are the AC current sensors, which are of the same type as the DC sensor. So moving on to testing, the first step of our testing after just a basic low voltage power up and verifying that the controller and all of the auxiliary power supplies are functioning was to do a double pulse test. If you're not familiar with this type of test, it is a pretty simple way to verify the function of switches on an individual basis. An inductor is connected in series with the switch, and the freewheeling diode of the other half of each half bridge allows that inductor to continue passing current after the switch is off. So the switch under test is turned on and the current ramps up. And then when you reach the desired current value, you turn that switch off and then shortly later back on. And so then you have switching transients in both directions at the desired current level. So this just kind of verifies that all of the hardware is working correctly and also gives us a chance to look at the single event switching losses. Once that was done for all six switches, we moved on to an inductive load test. In this test, we use a purely inductive load so that we can reach our maximum phase currents and check operation without requiring a large DC power supply. In this case, we used a simple, just a rack mount 15 amp supply at 1000 volts. And this large utility line inductor as the load. Our measurement setup is a typical power analyzer. but with the addition of these limb current transducers and an interface box. So these current transducers are available at just about any current level that you want. In our case, they're 700 amp rated, and they produce a much lower current output that can be read by the power analyzer. And so here is a screenshot of that power analyzer showing the inverter operating at maximum current output of 480 amps RMS. After verifying that functionality, we move on to the resistive inductive load test. This is the most accurate to real world conditions test that we can do without using a dyno. We select the inductor and resistor values to get us in the ballpark of the power factor of an electric machine, operating at the desired torque and speed. Measurement setup is the same with the power analyzer and current transducers. This time the power supply required is much larger. We're using 2 of these cabinet style 650 volt 240 amp power supplies in parallel. The inductor is still in play here, now just in series. And then we assembled a special resistive load bank for this test. It has many individual resistor strings that can be configured for the voltage rating and resistance that's needed. In total, this can handle up to 500 kilowatts, but we've configured it for 250 kilowatts at our voltage and current level. So here is an output of the power analyzer during that test. You can see we're reaching that same max phase current of 480 amps RMS. DC voltage we limited to 600 volts to give us kind of that worst case scenario. Again, the lower DC bus voltage is higher stress on the devices for a given power output. And then our phase voltage is 242 volts RMS. One thing I will note is that the power analyzer is applying a low pass filter to these measurements. Obviously the phase voltages are not going to be nice sinusoidal, they will be square wave PWM. So we're low pass filtering that so that we can see the fundamental here. And that will actually change slightly the power output measurement that we're getting. And which power output measurement is correct is kind of up to your definition. Without the low pass filter, you will see the true output power of the inverter. That's coming from both the fundamental and also any higher harmonics of voltage. That output power is real. However, it is not usable to the motor. The motor can only generate torque based on the fundamental output voltage. And so if you want to see the usable output power of the inverter from the motor's perspective, that low pass filter will show you. So here is the numeric output of the power analyzer with that low pass filtering on. Again, the DC bus is at 600 volts. We're running a 250 hertz fundamental and power factor just under 0.8. Under maximum output conditions, we're reaching 265 kilowatts, which is over the 250 kilowatt continuous goal. And our apparent power is 343 kVA. Under normal power output conditions of 250 kilowatts, we reached a peak efficiency of 98.6%. So in summary here, our inverter was able to achieve 114 kVA per liter and 21.2 kVA per kilogram. These are pretty conservative numbers. A lot of times the power density ratings will not include the casework or some of the extra hardware, only the power stage. But in our case, this is including everything you saw in the picture. We were able to exceed the 98.5% efficiency target. And the next step for this inverter, several of those inverter prototypes were tested at Freedom and verified to work, and now they are ready for road testing in the vehicle. So they're actually being installed in an actual semi that will drive around following that route, and we'll be able to see what the efficiency is and the reliability as well. So I just want to highlight some of the strengths of the Freedom System Center. Throughout this project, we worked really closely with our industry partner and provided them a lot of support. And that took the form of just general technical expertise, simulation support. We ran a lot of different simulations on both hardware, software, and system level. And then we also helped them with their software development that would run on the microcontroller in the inverter. Our ability to test at really high power is fairly unique. We can do all sorts of power testing. We have a lot of equipment and as well as measuring devices to get accurate results at those power levels. And as I mentioned before, we can collaborate really closely with industry partners and work with you and provide a lot of value, whether that's technical help or hardware testing throughout that design and prototype process.
Michael, we did get, yeah, it's time for questions.
Great.
Yeah, so what was the final switching frequency for the inverter?
Yes, should have mentioned that. We landed at 20 kilohertz. Again, this value was kind of a trade-off between keeping those passives minimized in size, particularly the DC bus capacitor, and the limitations of the traction motor. A higher DVDT can be harder on the motor insulation and on the bearings. And also, again, as I mentioned, power losses going up at higher switching frequencies as well.
And did we measure that DVDT?
We did, and again, I don't remember the value offhand, but could share that with you later if needed. Okay.
Okay. But like you said, that's a trade-off in determining that operating frequency for the inverter.
Yeah, absolutely.
Yeah. And then is this a direct connect to the motor, or is a sine filter required?
There's no filter, it's direct connect.
And for those of us who are not really familiar, how does a sine filter work?
A sine filter, most likely a LCL filter, will take that square wave output of the inverter and just smooth it to be sinusoidal. That way, the high VDT is really only seen in the filter, and it keeps it totally out of the motor. From the motor's point of view, then the input will be more like what you'd see, grid connected or something, a nice pure sinusoidal.
Okay. Okay. Good explanation. So here's a question. What is the fundamental frequency range for the entire operating range of speed?
Fundamental frequency from 0 to 1.1 kilohertz.
Okay. And then do you have any data on common mode noise measurement on the DC side and inverter output?
I believe we did some measurement of that, but again, I would have to follow up on actual numbers.
And are any of these questions answered in the paper that you have listed as a reference?
This reference paper was on the current sensors primarily. So I don't think that would provide much info on the two questions were DVDT, which that might have been mentioned in there, but common mode noise was not.
Okay. Okay. And I think you showed this earlier, but do we have any data on efficiency from 0 to 100% power range? You mentioned peak efficiency.
Yes, peak efficiency we measured in the lab. Overall, like across the drive cycle efficiency, we only simulated.
Okay. Do we have any plans to do that to measure the full drive cycle efficiency?
I'm sure it will be measured in the truck. But the efficiency target, that specific number was coming from the DOE, and that was just at max power output. So that was kind of the strict requirement. I think testing on a static load setup like we have, trying to capture that across the full range would be not very useful, just because testing in the actual vehicle environment would be a lot more informative. So I'm certain that will be done by the road testing people, but it's not completed yet, of course.
Okay. Good point. And you may have mentioned this. When do we expect to see results from that road test?
Good question. I know it was scheduled to start, I think last month, actually. And it's kind of a long-term test. So I guess preliminary results could come in fairly soon. But I think they want to test over the course of 6 months or a year to get the reliability.
Okay. And again, this was this in Long Beach? Or where was the testing taking place physically?
Somewhere in California.
Okay. All right. Somewhere in California. That's good enough.
I can't remember. It's either LA or San Francisco.
Okay. So we have another question here from the chat. You had mentioned using PSIM for inputting device details, but most of the simulations seem to be on Simulink and Plex. Where did the PSIM simulations play a part in the design?
So PSIM is much faster for hardware simulation, and a lot more detailed generally. So that was most useful in determining like worst case thermal performance. So if we want to look at maximum load, how much power is dissipated by the devices and how much is the junction heating, PSIM excels at that at the short time scale. Whereas Simulink is better if you want to kind of look at just broadly, like, for example, the system level Simulink simulation, we used a lookup table for inverter efficiency. So we're not actually simulating the switching events in Simulink. That would take a very long time. We're just looking, okay, the DC bus voltage and the current output from the inverter means that we're going to have roughly this efficiency. But that lookup table was generated based on PSIM thermal simulations. Okay.
And we have couple more questions here. The torque and RPM range was 36%. Did you mention it as an example and simulations were done on the complete range?
That was an example just showing that in a drive cycle, you have a lot of repetitiveness where you keep ending up at the same operating point throughout that 3.5 hour total period. So if you can simulate what the inverter efficiency is in that range, then you can apply that efficiency through that lookup table method that I just mentioned to the whole 3.5 hour simulation, rather than trying to re-simulate the inverter's efficiency every time it reaches that certain torque and speed value.
Okay, right.
Hopefully that makes sense.
Yeah, well, I mean, it's a method of simplifying the simulation requirements to be able to find the right points to design around.
Mm-hmm.
Yeah. So here's a question about getting more detailed information about the systems design and other aspects. Maybe in a future paper. Are there future papers planned on this project?
I don't think anything's planned on this project yet.
Okay. Okay.
The final testing that I mentioned in the truck that's handed off to Ricardo. We're not completing that, so.
Okay. And partially that reason, I mean, normally, when FREEDM does a project funded by the Department of Energy, we'll write as many papers as we can. In this particular case, right, we were kind of a subcontractor or a partner on the project. And so Ricardo
Right.
is the lead, is the one that's doing any of those high level analyses or, additional publications on this.
Exactly, yeah.
Yeah, okay, okay. So here's another question. Could you please talk a bit more about the size of the link capacitors and switching frequency? That is, are the caps sized based on torque changes or pulsed current from the drive?
Okay, so that is kind of dependent on your application. So if you are expecting a big torque transient, then it may be necessary to store enough energy in that DC link capacitor to cover that transient. In our case, automotive application, especially for a large truck, there's no real need for a huge instantaneous change in torque output. So that bus capacitor is not responsible for large amounts of energy storage. It's really just smoothing the cycle by cycle level of ripple. You're correct that if you were going to expect large torque transients, then the DC bus capacitor is sized more for that than it is for the switching frequency level of ripple. But in our case, that's not as relevant.
Okay. And here's one more. And I would, everybody seems to have this down, but if you do have any questions, please put them in the chat. So why was the drayage drive cycle selected? And are there any other standard drive cycles for Class 8 trucks?
There are other standard drive cycles, but in our case, this project is coming down from the DOE, and the DOE specifically wants a drayage truck for the port of whichever city it was. So it's known that all of these inverters are going into trucks in that specific application. So that's why we didn't really look at anything else. This is kind of a niche application. And I don't know, Minky, could you comment on other standard drive cycles?
Yeah, there is one drive cycle for the 8 class truck. So we did some simulation for that drive cycle, but the company want to see the drive cycle simulation at that real load. So that's why Michael showed that result.
But there are, if people wanted to learn more about just drive cycles in general, is there a good reference for that?
It is very, yeah, I mean, it is very hard to say, but for the general study, I believe the standard drive cycle for the Class 8 truck is better than this real load drive cycle.
Okay. I mean, in a previous role, I did some work with school buses, and we were always talking about different school bus drive cycles.
Okay.
So, for the person who asked the question, there are, I would say, dozens of different drive cycles, but there are some standards that are adopted by certain industries to judge that are, deemed most common. Just like Michael said, we picked one that was particular to this particular application, but there are a lot of different standards out there for evaluation. And we have a excellent work comment from one of our frequent questioners.
Thank you.
Yeah, so I do appreciate your time, and this has been a really good presentation. And thanks to you and Mingy and the whole team for all of the work that you guys did on this project. I think it's been a really successful project, demonstrated a lot of capabilities of FREEDM for the high power testing and other applications. And so there is one question here about the webinar, which is a nice segue. So this will be, we are recording this. It will be posted to the, like I said, the NC State Electrical and Computer Engineering YouTube channel. And I will send out a note to all of the registrants as to when that is available. Usually it just takes a day or two. So I want to thank everyone again, and we will end the webinar. Thank you, Michael.
Thank you very much.